Nitrogen is compressed isentropically from 100 kilopascals and 27 degrees Celsius to 1000 kilopascals in a piston cylinder device. Determine its final temperature. So let's start with our setup. First of all, it says that we have a piston cylinder device. We have nitrogen, and it says that, so it tells us, first of all, it says that it's compressed isentropically. So we know that S2 is equal to S1. And it also tells us what P1 and P2 are. So P1 is 100 kilopascals. T1 is 27 degrees Celsius. And then it tells us P2 is 1000 kilopascals. And T2 is what we're looking for. So I'm just going to put a question mark on that. So since we can really get this a couple different ways, and I think one thing that gets kind of confusing with solving these types of problems is there's multiple ways to do them, and so it can just can get kind of confusing. Since this example is for isentropic relations, that's the way that I'm going to use to solve this. But either, since we know that S1 is equal to S2, I'm just going to write that. So since S1 is equal to S2, since it's isentropic, we can look up data. There is a table for nitrogen. Or, so we can look up data, or we can, since this is an ideal gas, we can use one of the isentropic relations. So the reason why we can use the isentropic relations is because this is an ideal gas and it's isentropic. So let's go ahead and make some assumptions, and we'd probably want to look up the critical temperature and pressure just to make sure. So the critical temperature is 126.2 Kelvin, and the critical pressure is 3.39 megapascal. So just looking at our temperature and pressure, so we have a pretty high temperature compared to the critical temperature, and we also have a pretty low pressure compared to the critical pressure. So we can assume that this is an ideal gas. We're also going to assume constant specific heat. So we need both of these to be true in order to use the isentropic relation. We also need this to be an isentropic process, which we know it is. So now let's write our equations. So we're going to use the second isentropic equation for ideal gas, or second isentropic relation for ideal gas. So this is T2 over T1 is equal to P2 over P1 to the K minus 1 over K. Get our data. Really the only data that we need is K, and so we're going to just look up K at 300 Kelvin is equal to 1.4. And so really, so we know T1, we know P1 and P2, we know K, so it's really just a matter of plugging everything in. So let's do solve. So T2, we're looking for T2, T1, 27, we want these temperatures to be in Kelvin, so 27 plus 273 is equal to 1000 kilopascal over 100 kilopascal to the 0.4 minus 1 over 1.4. And so then if we solve this, T2 is equal to 579 Kelvin. So one way that we can take this a little bit further, we have, so before, when we looked up the data the first time, we really only had the one temperature, so we just kind of assumed room temperature. But now we have a temperature that we can use to calculate an average temperature. So what we can do is we can calculate an average temperature and then look at K at the average temperature and then resolve to get T2. So let's do that. So T average is equal to 579 plus 300 divided by 2, which is equal to 439.5 Kelvin. And so then K average at 439 Kelvin is equal to 1.397. So then we can resolve this. So T2 over, and now we have, so we still have 300 Kelvin for T1 is equal to 1000 kilopascals over 100 kilopascals, and then this is to the 1.397 minus 1 divided by 1.397. So then this works out to T2 as 577 Kelvin.